So we've now seen how to lexicalize a tree bank, how to add these lexical annotations to each non-terminal in a tree bank. Next, let's talk about lexicalized probabilistic context-free grammars. I'll give some basic definitions. Okay, so firstly, to recap, let's remind ourselves of context-free grammars in Chomsky normal form. So a CFG in Chomsky normal form consists of the following. N is a set of non-terminal symbols in the grammar. Sigma is a set of terminal symbols or words. We have S, which is a distinguished start symbol, which always occurs at the root of the tree. And then finally we have a set of rules R, and each rule in R must take one of two different forms. So it either has the form x goes to y1, y2, where all three elements x, y1, and y2 are non-terminals. So an example would be s goes to np, vp. Or it consists of x goes to y, where x is a non-terminal and y is a word. So for example, dt goes to there. And we saw that given a PCFG in Chomsky normal form, we can use dynamic programming to find the highest probability paths in order cubic time in the length of the sentence. So n is the length of the sentence, and cubic time in the number of non-terminals in the grammar. So here's a definition of lexicalized context-free grammars in Chomsky normal form, which is closely related to the definition I gave you on the previous slide. So with a lexicalized CFG, we again assume we have some set of non-terminal symbols, we have a set of terminal symbols, and we have a start symbol. But the rules in the grammar take a slightly different form. So there are three different cases. Let's go through the simplest case first. So this says that we can have a rule where x is a non-terminal and h is a word, where xh rewrites as h. So for example, dt there goes to there is one example of this rule, where x equals dt and h equals there. So these are the rules seen at the very leaves of the tree, where a part of speech with some lexical item simply rewrites as that lexical item. Now let's look at these two remaining cases. Let's look at this one first. This says I can take any three non-terminals, x, y1, y2, and any two words, h and w, and I can have a lexicalized rule where xh rewrites as y1h, y2w. Let me give you an example of such a rule. We could, for example, have vp soar goes to vt soar np dog. Now critically, I'm going to subscript these arrows. This has a 1 here to specify which of the two children is the head of this rule. So because soar is on the left-hand side of the rule and soar is here on the first non-terminal, I subscript the arrow 1 to say that that's where this head word came from, that this is the head of the rule. So in this particular example, we have x equals vp, y1 is equal to vt, y2 is equal to np, h is equal to soar, and w is equal to dog. This case is similar. So let me give an example of this rule. This, for example, could be s soar goes to 2 np man vp soar. Notice in this case the head word comes from the second child, and that's why the arrow is annotated in this way. So this annotation on the arrows is sort of a pesky detail, but it's important. And it's important because it avoids ambiguities. If, for example, I have np dog goes to nn dog, very unlikely, but possible, where the h is equal to dog and w is equal to dog, we're just going to be careful to specify which of these two children the head word came from. So here's an example of a lexicalized context-free grammar in this Chomsky normal form. And let me show you a parse tree under this. So we have S sor goes to, for example, NP man, VP sor, and we'll just mark this to say that this is where the head came from. This is the head of the phrase. And then NP man could go to DT there, NN man, for example. So I've used this rule, and now I'm using this rule. Again, let's mark the head. And then we have there, man, and we could go on and on. So we have derivations with these lexicalized context-free grammars, which look very similar to derivations under regular context-free grammars. We just have head words associated with each of these non-terminals in the tree. So we will introduce parameters or probabilities in these lexicalized PCFGs. It's important to emphasize the similarities and differences from regular PCFGs. So in a regular PCFG, we saw parameters like the following. For example, Q of S goes to NP-VP. This is basically the conditional probability. Given that I have an S, there are going to be multiple ways of rewriting that S. NP-VP is going to be one of them. And this is going to be the probability that we choose this as opposed to all those other alternatives. We have parameters in lexicalized PCFGs, which again are associated with entire rules. So here's an example parameter. And now this parameter is for the rule S sor goes to NP man VP sor. So this again is going to have an interpretation as a conditional probability. In this case, the interpretation is, given that I have S sor on the left-hand side of a rule, there are many, many different possibilities. One is to choose the second non-terminal as the head, and to choose NP man, VP sor as the two children. And there are going to be many, many other possibilities. So there are definite similarities between these two models. In fact, technically speaking, a lexicalized PCFG really is just a special case of PCFG. But qualitatively, something has really changed, which is that we've gone from a relatively small number of parameters in this original model to a very, very large number of parameters. We have one parameter for every possible lexicalized rule. And so we're going to have to be very careful in how we estimate the parameters of these models. But we'll see that the smoothing techniques you saw for language modeling in the very first segment of this course can be applied very, very directly to this problem. Next, let's talk a little bit about parsing with lexicalized CFGs. I don't want to go into tremendous detail about parsing algorithms for lexicalized PCFGs, but I want to give you a sketch here. The main point being that you can use a very, very similar dynamic programming algorithm to the dynamic programming algorithm we saw for regular PCFGs. So the new form of grammar I've just shown you is very similar to a Chomsky normal form CFG. But whereas before we had rules like S goes to NP-VP, so there are order n cubed possible rules where n is the number of non-terminals, so I have n times n times n. In this new grammar I have things like S sor goes to NP dog VP sor. And so if I think of the number of choices, well, I have three non-terminals here, S, NP, and VP. So I have n cubed choices there. And also in each rule I have two words, the head word sor and the modifier word dog. And so I'm going to have sigma squared. And so there are many, many possible rules. Okay, so I've gone from a grammar with order n cubed rules to a grammar with this many rules. So naively, you can just pick up the dynamic programming algorithm we saw for probabilistic context-free grammars and apply it to this new grammar. These rules are really just like regular context-free rules. We can just treat these as non-terminals. We just have a much larger set of non-terminals than we had before. But But if you do this naively, you'll end up with the following running time. Remember, before we had order n cubed times number of non-terminals cubed as the runtime for dynamic programming. This is our new runtime, and we have sigma squared coming in here. This is a terrible idea because the vocabulary size can be huge. Sigma could easily be on the order of hundreds, or much more likely thousands, or even tens of thousands. But there's a simple observation which gives us at least a plausibly efficient algorithm. If I have a particular sentence, like the dog saw the cat, I can immediately discard rules such as the following. So S questioned goes to NP dog, BP questioned. I can immediately discard this rule because it has a word questioned in one of these non-terminals, which is seen nowhere in the sentence. So we know that rule can never be used in parsing this sentence. And so we can actually restrict ourselves to a much smaller set of rules, where we now have order n squared times n cubed, because, again, we have capital N choices for each of these three non-terminals. And then these two words, rather than being drawn from the full vocabulary, have to be drawn from one of the n words in the sentence. Okay, so we end up with a much smaller set of rules just by restricting the grammar in this very simple way. And this is actually going to lead to a runtime of order n to the fifth times n cubed. Where does this come from? Well, we have order n cubed. It's a dependence of the dynamic programming algorithm on the sentence length. And then we have to multiply in the number of non-terminals or rules in the grammar. And so this is where we get order n cubed times n squared. It's the number of possible rules, and so this is the runtime we get. So that's really more of a sketch than a precise definition of the algorithm, but hopefully you'll get the idea. And the important point is that you can end up parsing with these lexicalized PCFGs relatively efficiently. We now have gone from an n cubed dependence on the sentence length to an n to the fifth, and so that's expensive, but it's still manageable if you're careful about how you do things.